All right, so the first two problems are pretty similar. Again, so what I mean by that is they have the same circuit, right? So for 1 and 2, the circuit looks like this, and you know everything. In other words, you know the voltage of the battery and all the resistors. So the first question is, for both questions actually, but the first question is, what's the total power dissipated by all the resistors, excluding resistor 2 and 4? So here's resistor 2, here's resistor 4. If you figure out the power dissipated by all of them, except those two, what does that equal? So, it doesn't matter how you do it. There's actually two different ways to do it. But regardless of how you do it, either way, you have to figure out all the currents in the circuit. That's the first thing you need to do. For both questions 1 and 2. So does anyone know how you do this? It's a combination circuit, by the way. It's not a Kirchhoff's thing, right? So if there's one battery and then connected to a bunch of resistors like this, it's what we call a combination circuit. And so there's this recipe for doing combination circuits. Does anyone remember?
Oh,
No, not the loops. That's actually number 3 is the loops. This is like before we did loops. It was in lecture 10, maybe? Well, I can look. Sorry. All right, so lecture 10. Let's see, is that the one? Yes, that's the one. So we had this example, right? And it's the same thing. I mean, obviously the circuit's different, but essentially it's the same thing. So what are the steps here? So the first thing you have to do is what we did in part A, right? What's the equivalent resistance of the entire circuit? So what do we do? All right, so first you have to draw the currents, right, in the circuit. That's step 1. And the reason why we do that is because you want to figure out which are in series and which are in parallel. So let's do that. I'm going to go back and forth between these two. Actually, I'm going to open up another thing to make it easier if I can do it. All right. I'm going to go back and forth between lecture 10 and this review session. All right, so the first thing I'm going to do is draw the currents in here, right? So what do the currents look like? So you have that battery, right? So this one, you know exactly what the current's doing because there's only one battery. It's not like you have to guess which way the currents are going. You know which way the currents are going. So which way do they go for this particular case here?
away from the positive.
Right, so there's a current here. Let's call this current I, right? And then this current goes through here. Oops. Okay. And then what happens here? Right, so this is no current. Oops, well I missed the line, but you get the idea. So that's different current. You can call it whatever you want to call it, but I always call it I1, right? In every single example I've done, so I call it I1. And then what is the current here? Is it the same as these two currents, or is it a different current? The current that goes through, say, the R4 and over here. Yeah, but is it the same? Is it I or I1, or is it something else? It's another current, right? It's not equal to either of the other two currents, right? So this is like I2, right? I mean, you can call these things whatever you want to call them. You can call them I prime and I double prime or whatever. But I always call them I1 and I2 because it just makes sense to call it I1 and I2. So this is I2. And this is I2. And then when they hit this point here, what's this current, say, through R8? Right, it's the original current coming out of the battery. And of course, this continues to go through the battery. So what we really want to do is find, these three currents. But to do that, you first have to find the equivalent resistance. And the first find the equivalent resistance, the first step you have to do is, well, we did the first step, but the first step after drawing the currents is what I meant to say, is you have to identify which are in series, right? So for this case, here resistors 2 and 3 are in series, and 4 and 5 are in series with one another. So why is 2 and 3 in series, and 4 or 5? I mean, there's two ways to look at it. One, you can see they're in series, but the better way to look at it is, well, what's another way to look at it, why they're in series?
So why are 2 and 3 in series?
Yeah, so like for this example that we did in the notes, right? That we did in lecture 10.
Oh, it's the same current?
Yeah, it's the same current going through them, right? I1 goes through R2 and R3, I2 goes through R4 and R5. But different, you know, R1 isn't in series with either one of them because there's different currents, right? Going through R1 and R2, for instance, and R1 and R4. So if you go back to the example in the homework, which are in series with one another, right? R1 and R8. Yes. So let me just say something. R1 and R8 are in series because the same current of I goes through them, right? And R2 and R3 are in series because I1 goes through all of them. And what else? Yeah, so 4, 5, 6, and 7 are also in series because I2 goes through all of them. So that's the first thing you got to do is combine the ones that are clearly in series with one another. So how would you figure out, if you combine resistor 1 and 8, so they're in series, how would you do that mathematically speaking? Like what would you do? Yeah, right, you just add them, right? So I'm writing everything down here, and I hope everyone understands what we're doing and not just doing these calculations blind again, like I think at least half the class does. Okay, so R2 and R3 are in series, so you just add them. Right, I mean, but this is easy, I think, for everyone, hopefully. If things are in series, you just add them together, right? That gives you the equivalent resistance in series. It's not that hard of a concept to understand. It's one of the easier concepts when you're analyzing circuits, right? To add resistors in series. All right, so now you have the equivalent resistance of 1 and 8, 2 and 3, and 4, 5, 6, and 7. Now, I will admit, you got to be careful because, you know, all the resistances are just listed out. So you want to make sure you're adding R1 and R8 and not, say, R1 and R7 because you look at it too quick. That does happen. It happens to me every once in a while. I look at the resistances too quick and see R8, you know, the value for R7 when it's supposed to be R8. But you just got to go through it carefully. Okay, so then what's the next step, right? So let's go back to the notes. Okay, so that's what we did here. And then when you do that, you replace one of the resistors with the equivalent resistors, and you have a circuit like this, right? So it's a little bit different for us, but it looks like this for us. So I'm just going to put V here, because the battery is different for everyone. But this is like R18, so you could say, well, how come you didn't replace resistor 8 with, you know, how come you didn't put that resistor here where R8 was? It doesn't matter. You get the same answer either way. You just replace one of the resistors with the equivalent resistors, right, that you combine. It doesn't matter where you put them. And then this one, so you can ask the same question here. You know, how come you didn't replace, you put the equivalent resistor where R4 was or where R7 was? Once again, it doesn't matter, right? You just replace one of the resistors with the equivalent resistor, you get the same answer. So this is the simplified circuit when you combine the resistors, series resistors, sorry. All right, let's go back to the notes. All right, so this is what we did here. And the next step is combine things which are in parallel, right? So for the notes, you know, in lecture 10, R2 and R2, 3 and R4, 5 are in parallel, right? And you know, you combine them like parallel. So what is it for our case? Which ones are in parallel for our example here? Yeah, once again, because if you find the voltage here, right, it's the same voltage here, correct? Because there's no resistors between them. And the voltage here is the same as the voltage here, right? Because there's no resistors in between them. So the voltage across each one of them are the same. And therefore they're in parallel. That's the real reason why they're in parallel, because they have the same voltage. Or you can just look at it and it looks like they're in parallel. So that's another reason. So what's the equation for parallel, though? If you combine two resistors, you essentially have two resistors here, which are in parallel, right? So how do you do that? I mean, you just saw it. You just did it, and you just, something like that, right? So what would it be for this case? So you're combining, resistor 2, 3, 4, 5, 6, 7 together. So what would it be? If you knew what R23 was and R4, 5, 6, 7 was, how would you find the equivalent resistance if they're in parallel? Yep. But you have to do one more thing. Yeah, right. Okay, so now you combine these two into one resistor, which is what we did in the notes, right? Sorry. That's what we did here. And now the circuit looks like this, right? So our circuit will look like this too, because you combined, you're basically smashing these two resistors together. So what this resistor becomes is R2, 3, 4, 5, 6, 7, and this one is still, this is R18, and this is just the voltage of the battery. So now you just have two resistors that are what? Are they in series or are they in parallel? Series. This is how it always works. It goes series, parallel, series. It's the same steps for everything. It's always series, parallel, series. So then how do you figure out the equivalent resistance of the whole circuit, which is essentially, combining every resistor in the circuit? You just add them up, right? So then it's R18 plus R2, 3, 4, 5, 6, 7. So it is a little bit of work, but it's the same steps, right? I mean, and these things aren't super hard to calculate. You're just adding things for the most part. There's one little minor step here where you have to take, an inverse, right? But besides that, it's pretty straightforward. You're just adding things up, right? Okay, so now we have the equivalent circuit, resistance of the entire circuit. Now what we're going to do is figure out the currents, right? So that's what we did in lecture 10. So look, we found the equivalent resistance, right? That was part A. And then part B, well, what is the voltage across resistor 1? But to do that, we had to find the current going through resistor 1. So this is how you find the main current coming out of the battery all the time, for any circuit, right? For parallel, series, or combination. The easiest way to find the current coming out of the battery, I, not I1, not I2, but I, the current coming out of the battery, is by this equation here, because essentially you have the battery connected to one resistor, so you can find the current going through that resistor, and therefore it's the current coming out of the battery. So this is the next step. You use this equation here to find the current coming out of the battery. All right? So you know Req, you know V. It's given. The voltage of the battery is given. You just found Req. So the only thing you don't know is I, right? So that's I. Okay, so now you know I, correct? But I is the current coming out of the battery. We still need to find I1 and I2. All right, so let's see how we do that. Because we did it here, so we found I. Okay. So to find I1 and I2, we had to do what we did in part C, which is the voltage across what I call the back of the circuit. In other words, for this case here, R2, 3, 4, 5, if you go back to the original circuit, was the whole back of the circuit, right? R2, 3, 4, 5, right? So I call this the back of the circuit, like the whole thing, the whole second loop is the back of the circuit. And to find the currents, I1 and I2, we need to find the voltage across the back of the circuit next, which is this thing that we did here. So there's two ways to do it. One way is you just use Ohm's law, because you have the, you know the current going through this equivalent resistor, right? So if you multiply the current through this resistor, you get the voltage across it. The other way to do it is you take the voltage of the battery and you subtract the voltage that you lose through the 2 ohm resistor. And that gives you the same answer. We did it both ways. It doesn't matter which way you do it. Let's just do it this way. So the next step is to find this, which is the voltage. I always call it, like I said, the back of the circuit, of course. For us, it's a little bit different. So the back of the circuit would be 2, 3, 5, 6, 7. And that would be the current that you just found times R, 2, 3, 4, 5, 6, 7. And you know what this is because you found it here, or whatever number you got here. For the resistance, you multiply it times the current. Right, so that goes, this goes in here. So now you know the voltage across the back of the circuit. What's the next step? Okay, so what's I1 and I2? This is what we're trying to find so we can answer this question. So when you go back a step, right, the voltage across the back of the circuit in this particular example is 5.56 volts. But when you go back a step to the previous circuit diagram, that means the voltage across all the resistors in the middle, for this case R2, 3, and the voltage across all the resistors for the other part of the loop is the same, because it's the same voltage. I already went over this. So you can use this to find I1 and I2. How do we do it? The voltage across here is the voltage at the back of the circuit, so you divide it by 5 ohms, and that's I1. And then you do the same thing, you divide it by R4, 5, and that's I2, right? The voltage at the back of the circuit divided by the resistances, right? There, give you the currents. So for this case here, if we go back to this step, let me copy this down here because it's easier to see if we go look at this circuit here. So what you just found is V2, 3, 4, 5, 6, 7, which is kind of a pain to write down. But the point is, this voltage here is equal to V2, 3, 4, 5, 6, 7, right? And this voltage here is the same thing. It's V2, 3, 4, 5, 6, 7, because there's no resistors there, right? And the voltage here is 0, the voltage here is 0, and the reason why it's 0 is because it's connected to the negative end of the battery, right? So what I'm trying to say is you know the voltage across this resistor, which is R2, 3, and you know the voltage across this resistor, which is R4, 5, 6, 7. And, you know, the current going through this part of the circuit is I1. The current going through this part of the circuit is I2. So if you want to find the current in each of those parts of the circuit, I1 would be V2, 3, 4, 5, 6, 7, divided by whatever you found for R2, 3. And then I2 is the same thing, except you're dividing by R4, 5, 6, 7, because that's the other resistance. So this would give you I1 and I2. Now, one thing you can do to check to make sure your answers make sense is if you take I1 and I2 and add them together, what do you think you should get? I. So that's actually something good to do to check to make sure you're doing things right. If you get a different number than I, it means you're doing something wrong, right? Something is miscalculated somewhere along the line. Okay, so for both 1 and 2, you do exactly these steps. It's a few steps, yes, but it's the same steps for both of them. And you're just adding and dividing. I mean, they're not like crazy hard math, right? To get I1 and I2. I mean, yes, there are a lot of steps, but most of them are pretty simple math. Okay, so now we have I1, and I2. Now the question is, how do we answer the final question for number 1? So there are 2 ways to answer it. One way is easier than the other way. So I'm going to tell you the easy way, and then if you want, you could do the harder way, but you'll probably do the easy way. So the question is, what's the power? Just, you might have forgot the question. It's what's the total power dissipated by every single resistor except for resistor 2 and resistor 4. So the hard way to do it is if you know the currents going through each resistor, you could find the power dissipated by each resistor. So for instance, how would you find the power dissipated by that resistor, R1? How would you figure that out if you knew all the currents, right? You know I1, and I2 now. So the question is, how would you figure out the power dissipated by resistor 1? Yeah, it's I squared R, right? You're always using I squared R set for parallel circuits, where it's V squared over R, right? So, but there's three different currents, right? So the current going through is I, right? Not I1 or I2, so it'd be I squared times R1. How would you find, say, the power for R3? Yeah, but which current do you use, just to be clear? The I1 squared times R3. What about R4? I2 squared times R4, right? So you could do that for all the resistors, except for 2 and 4, and get an answer. Or an easier way to do it is, what's true if you could figure out the power of the battery? What is that? How does it relate to the power dissipated by all the resistors? So, first of all, how do you find the power output of the battery, if that were a question? The current going through it times V, or the current coming out of it times V, right? Okay, so the question is, you could figure that out, right? It's easy to figure out. It's just multiplying two numbers together. So how does that relate to the power dissipated by all the resistors in every single circuit? It's equal to, right? So if you take all the power of all the resistors dissipated, technically, by all the resistors and add them up, it's equal to the power output of the battery. So an easier way to do it, instead of finding 8 different calculations for 8 different, or 6, I guess, 6 different resistors, is to find the power output of the battery and then just subtract the power from R2 and R4, and then you just have to calculate 3 things as opposed to 6 things, correct? So once again, how do you find the power output of the battery? One more time. It's I times V, right? How do you find the power for R2? I1 squared times R2. How do you find the power for R4? Right. So the easiest way to do it, where it involves 3 calculations as opposed to 6, is, I don't know what you want to call it, P prime. I don't know. It's not total power, because you're subtracting 2 resistors, but it doesn't matter. It's the power of the battery, which is I times V, minus the power from R2, right? It's 2 and 4, minus the power from R4. And I said it, but you should know it. The PV is IV. P for R2 is I1. Wait, where's R2? Yeah, I1 squared times R2, and the power for R4 is I2 squared times R4, right? So you need all 3 currents to do the question. So that's it. That's how you do number 1. So number 2 is the same thing. And you do the exact same steps again. Sorry, to figure out the currents, right? So you basically repeat what you did in 1 to find the currents. I forgot to draw 2 things here, but they're easy to draw. And then on the second circuit diagram, you have this here. You have a X here, A, and you have a X here, which is B. Okay, so first, all right, repeat 1 to find all the currents. Okay, so assuming you did everything that we did in 1 and you found all 3 currents again. Actually, let me go back to 1, because it's just easier if I copy this one and redraw those 2 X's again. So the current looks like this, and you know all the current. The circuit looks like this, and you know all the currents because you just did all the steps that you need to do to find I1, and I2. And all right, so the question here is, what is the voltage at this point, which I called point A? And the question is, what is the voltage at this point, which I called B? And then the question is, what's the difference of those currents? Voltages. Sorry. When I say currents, I mean find the voltage at A, voltage at B, and then find the difference between the 2. Subtract VB from VA. So this is not so bad if you know all the currents. So what's the voltage like right here? Like, like right after the battery. Voltage of the battery, right? But what happens when you go through a resistor, specifically with the current, right? Do you lose voltage or do you gain voltage? You lose. The question is, how much do you lose when you go through a resistor 1? So you start with V, right? And then how much do you lose when you go through this resistor exactly? How do you figure out voltage across resistors? So it's something we use, right? Ohm's law, right? So how much exactly do you lose when you go through resistor 1? Exactly, if you know the resistance and the current, I.
Just multiply.
Right, multiply them together, right? But the point is there's 3 different currents, right? So you got to use the right current is what I'm trying to say, right? So it's I times R1, right?
Yeah, just
Okay. It's a common problem, though. People just use random currents for random resistors, right? You need to know which current's going through a resistor, else you get the wrong answers. So the point is the voltage at point A is the voltage of the battery minus the voltage across 1, which is V minus I times R1. Correct? That's how you find the voltage at point A. Now what you have to do is do the same thing for point B. There's a fancy way to do this where you actually don't have to calculate the voltage at point A. But I'm showing you how to do it sort of the straightforward way, which is less confusing than the fancy way. Right? So that's the voltage at A. Now, how do you find the voltage at B? Let's start at the battery again, right? Okay, so you have to go through resistor 1 again, so you lose voltage when you go through resistor 1. And then, so you might say, well, how do you get to point B? Okay, so one way to get to point B is I can go start here and then, or start here maybe, and then go this way to get to point B, right? Or I can go some crazy way. I can start here, go down the middle, go over this way, and then go up here, right? Or I can just take the most direct way, which is starting over here and going through these 2 resistors and getting here. So you could say, well, which way do you go? Okay, so it doesn't matter. You can go either way, any way you want. You get the same answer. So the trick is you go the simplest way possible, right? So the simplest way possible is you go from here through resistor 4, resistor 5, and then you end at point B, right? So we already went over, you lose voltage of I times R1 when you go through resistor 1. You obviously lose voltage, right, when you go through resistor 4, correct? Because you're going with the current. So how much voltage do you lose when you go through resistor 4? Right, I2 times R4. And then you lose voltage again when you go through R5. So how much voltage do you lose when you go through R5? Right. So what's the voltage at point B? V minus the voltage through resistor 1 minus the voltage, 4 and 5? Well, through resistor 4 and 5. So it's V minus IR1 minus, I2, right? R4 minus I2 R5. And that gives you the voltage at point B. And then you subtract them. Should the voltage at B, I mean, just mathematically speaking, if you look at it, should the voltage of B be less than the voltage of A? Do you think? Yeah. So if you subtract A from B, so the answer is like this, you should do this, right? This is like the change in voltage, well, whatever. That's what you're calculating, VB minus VA. So should you get a negative number or a positive number when you do that, do you think? Negative, right? Because VB is less than VA. Yeah, VB is smaller than A, right? But that's just how you do it, right? But you know, it's good to know like how you find the voltages across things, right? Resistors. It's good to know. All right, so that's how you do 1 and 2. A lot of the same work, just 2 different questions. Okay, so number 3 is like a Kirchhoff thing, but it's an easier sort of version of a Kirchhoff type problem. So what the setup here is, you know all the batteries. There's 4 of them. You know the voltages of all of them. You do not know the resistances except for one of them. The only one you know is R1. So you know the resistance of R1, but you know nothing about the resistances of the other 4 resistors, which is R2, 3, 4, and 5. So the question is, if you set it up the problem similarly to how we did it in class and described in the PowerPoint, meaning you choose V1 to guess the direction of the current flow, right? Remember with these type loop, Kirchhoff problems where there's more than one battery in the circuit, you have to pick a battery. In general, you're free to pick any battery, but of course, if everyone picked a different battery, everyone gets different answers, and you can't set up the problem, right? So this is how I told you it's going to be in the homework and for a test. If you have it on the test, it's going to be like this. So you're told to choose this battery so that everyone gets the same currents. And you're also told how to label the current. So the current through, the main current is the current through V1. All right, so let's just draw the currents, right? If you chose this battery to be the, how you're going to draw the currents. How would the current look if that was the only battery in your circuit? So what would the current be doing here first? How would it be coming out of this battery? Right. So I said call this current, I, the main current, right? So then this would be what? I, right? What does it get what happens when it comes to this thing, which is the junction? It splits up. So where does it, in the middle, where does it go? Does it go up or down, do you think? Up, right? So I said call this current I1. It's described in the homework question that should be I1, as it always is, and it's not any different. And then what is this current here? Is it going to be different than I and I1? Yeah, it's going to be I2, as we already did it, as we always do it. So, you don't have to know how to do everything associated with these problems, but you do not have to sketch the currents and then how to analyze the circuit if you know the currents, which I'll explain in a minute. But this part you need to know, right, is what I'm trying to say. So what is this current through R1? I. That you have to know, right? Okay. Now, I give you 2 out of the 3 currents. Again, just like we did in the lecture. So I give you I. So I is positive. It's different for everyone, but it's a positive number for everyone, right? So that's one thing that I give you. The other thing I give you is I2, and I2 is a negative number for everyone. So that means when you solve the correct equations, you get these 2 values for the currents. One's positive and one's negative. And the question is, what is the power dissipated from all the resistors except resistor 1? Okay, first, before we get to the answer to that, if you know these 2 currents, how do you figure out the third current, which is important?
Subtract I2.
Yeah, you always have this junction equation, right? Which you should know definitely for these Kirchhoff loop rule things, right? It's the most useful of them all. So if you're trying to figure out I1, which is the only thing you don't know because you know I and I2, it would be I, which is a positive number, minus I2, not I1, which is a negative number. So the question is I1 going to be a positive number or a negative number, or can you tell at this point? You can tell, I'll just say that. But is it going to be positive or? Remember, I2 is negative, right? Positive, right? Because you're subtracting a negative number, which makes it positive. So you're adding 2 positive numbers, essentially, right, when you do the algebra. So that's important. It tells you, now you know all the currents in which are positive and which are negative, correct? So it's very important for these things to know how to set up the problem and also know how to correct the circuit if one or more currents is negative. So we have only one negative current because I1 is positive and I is positive. So I2 is the only negative one. So you have to correct the circuit. So how do you do that? You have to know this, right, for these type problems, definitely on a quiz or a test, and obviously the homework to get this question right. So we have to correct the ones which are negative. So which one is negative? It is I2. I2 is negative, right? So how do you correct the circuit if I2 is negative?
Goes in the opposite.
Right. So instead of I2 going the way we originally guessed it, assuming that V1 was the only battery in the circuit, it actually goes like, that thing's like that, right? Now this is very important when you're trying to figure out the power of any of the batteries, or the total power of all the batteries. Because this is how we're going to finish this problem. So the question is, what is the power by all the resistors except for R1? And we don't know any resistor but R1. So you basically have to look at it the same way we did number 1. So what's true about the total power output of all the batteries in relation to the power dissipated by all the resistors? Again, just like it was for problem 1. Anyone remember what we said in problem 1? Yeah, but in general, right? So if you find the power from all the batteries, how does that relate to the power dissipated by all the resistors? V equal, right? Okay. So if you want to find the power dissipated by all the resistors except for R1, it's the same thing as finding the power from all the batteries and subtracting the power dissipated from resistor 1. So this is where correcting the circuit matters. How does it work for batteries? So if the current is coming out a positive end, is it a positive or negative power for that battery? Yeah. Right? But you got to correct the circuit or else you get there. So I is coming out the positive end of this battery, correct? V1, that is there. So this is a positive power. What about V2? Is it a positive or negative power? Positive. I1 is coming out the positive end. So this is the corrected current, right? We didn't need to correct I1, but in general, you got to correct the circuit because you need to find the actual direction of the current flow. What about V3, this one over here? Yes. And what about V4? Negative. Now, if you didn't correct the currents, you get opposite signs for V3 and V4, the power. Or some people don't know that they're negative powers, and every single battery would be positive. That's another common mistake. The other common mistake is that people don't use the right currents to find the powers, right? So what current do you use for V1? Remember, there's 3 of them, right? So what current do you use to find the power of V1? I. And what about V2? I1. What about V3 and V4? I2. Yeah, it looks like a 3, but it's I2, right? The second and the other current, right? So that's how you figure out the power for each battery. Remember, it's like an absolute value thing. I'll write one of them. I'm not going to write them all, though, because I want people to sort of think a little bit. I don't want to do every single step for them. But for instance, the power of V1 would be like I times V1 positive, right? I'll do, say, V4. No, I'll do V3. So it'd be like positive I2 times V3, right? That's what you're doing here, right? And for V4, it's negative. So it's like the negative I2 times V4. See ya. But anyhow, you can figure them out easy enough, right? You know all the currents, you know the voltages. So then what you do is you figure out the total power from all the batteries, right? So P total is PV1 plus PV2 plus PV3 plus PV4, which you can, it's just a number. So that's the total power output of all the batteries, but that also equals the total power dissipated by all the resistors, correct? Even though you don't know all the resistors, this is the total power from all the resistors too. So the question is, what is the total power dissipated by every resistor except the one that you know, which is R1? So then what do you have to do? You just have to subtract the power dissipated by R1. So how would you figure out the power dissipated by R1, once again, if you know the current going through it?
IR.
Almost.
I squared R.
Right. So then, I don't know how you would label this, but anyhow, it's P total minus the power for R1, which would be I squared times R1, right? And you know I, it's given. You know R1 is given. So that would give you the total power, the power from all the resistors except resistor 1, right? But anyhow, you don't have to solve the equations, but you do not have to do all this stuff. And I find a lot of people do not know like what I'm talking about here when I'm correcting the circuit and knowing which power is negative or positive, or how to find the power of any of the batteries because they use IV for everything. Like I, this I. Like the power of this one would be I times V. The power of this one is I times V. They use the same current for all the batteries, right? So you got to know which current goes through which battery. You got to know how to correct the circuit. You need to know how to figure out which power is positive or negative. You know, that kind of thing you need to know for the quiz or a test, right? Solving the equations you don't have to know. But this kind of thing you do have to know, right? Okay, so does that make sense? Okay, so then that ends the circuits like this. And then we're going on to capacitors in parallel series, but they're fairly straightforward questions. I think the last two are straightforward. The first 30, actually number 3 actually isn't too bad calculation-wise. 1 and 2 are a little bit bad because there's a lot of steps. But 3 is not that many steps, and it's pretty straightforward. And 4 and 5 are pretty straightforward too. Okay, so 4 is you have 3 capacitors connected purely in parallel to a battery, which you know. You know the voltage of the battery. You also know the charge in the second capacitor is some factor bigger than the charge in the first capacitor, and you also know the charge in the third capacitor is some factor less than the charge in the second capacitor, which we'll get to in a minute what that means. And you also know one other thing, which is the stored energy in all 3 capacitors. That's given. Total stored energy. And the question is, what's the charge in the third capacitor? Okay, first of all, we have 3 capacitors connected in parallel, correct? So before we even get into it, how do you figure out the equivalent capacitance if you have 3 capacitors connected in parallel? You don't know anything about them at this point, like what their capacitance values are. But the point is, this is in the Hlep lecture, which I don't have with me. It's on something else. This is in the Hlep lecture. Does anyone remember how you find the equivalent capacitance if they're connected in parallel?
Yeah.
Yes. All right, so that's one thing we can write down. So CEQ is C1 plus C2 plus C3. Now the only problem is you don't know any of those things. You don't know C1, C2, or C3, but you do know an equation which relates them together. All right, the other thing is you know the total stored energy, so it's also like at this. Does anyone? Probably not, because it's a little bit more involved than this. Okay, so let me see if I can find something similar to it quick. If I can't, I'll just tell you like the idea. So is it here? No, it's after this. Okay, so there are 3 equations for stored energy, right? This is one of them, this is one of them, this is one of them. So we know the voltage of the battery. It's given. And we don't know the equivalent capacitance, but we can use the total stored energy to find a capacitance. So the question is, if you know the stored energy and you're looking at these three equations, which is 1/2 q squared over c, 1/2 cv squared, or 1/2 q times v, which equation do you think we can use to find a capacitance if we know the voltage in the circuit? We know the voltage of the battery. So we know U, we know V, we're trying to find something related to C. So what's the best one to use? This one, right? So if you look at the Hlep video, we did use an equation like this to find the total stored energy. I just don't have it with me. But it's very similar to this, right? So the easiest way to find the total stored energy of a bunch of capacitors connected in parallel or in series, but particularly works good for parallel because the voltage is the same. This is the easiest way to find it, right? You take the equivalent capacitance, you multiply it by the voltage squared, divide by 2, that gives you the total stored energy. So the point is, we know U total, we know V, so what can we find with this? CEQ, right? So now we can find CEQ. This is the first step to find CEQ using this equation here. Okay, so we know CEQ. Now the question is, how do we figure out what it is we're trying to figure out? Okay, so how does charge work in a capacitor? So in other words, if you have a capacitor connected to a battery, how do you find the charge in the capacitor? It's in the same, right? This is it, right?
Yep.
Q is CV? Okay. So the next thing we're going to do is look at this equation here to finish this. So you don't know the charge in each capacitor exactly. However, you do know something about how much charge one has in relation to another one. Okay, which I'll get to in a second. But the first thing is the voltage is the same because they're connected in parallel, correct? Just like resistors. If you have resistors connected in parallel or capacitors, the voltage across them is the same. It's whatever the voltage of the battery is, correct? Just like resistors, it's the same thing. So the question is, how does the charge relate to the capacitance? So the voltage doesn't change. It's basically like a constant, right? So the question is, if you say make the capacitance bigger, what happens to the charge? Bigger, they're proportional, right? Make the capacitance smaller, the charge goes down. So you know how the charge in each capacitor relates to one another. That means you know how the capacitance relates to one another, right? Because they're directly related to one another. So suppose you start with C1, right? You don't know what C1 is, but you could figure it out somehow, which I'm going to explain. The charge in C2 is some amount bigger, some factor larger than the charge in C1. So what does that mean about the capacitance of C2 compared to C1? So if the charge in C2, right, is some factor bigger than the charge in C1, what does that mean about the capacitance? It's the same factor bigger, right? And the charge in C3 is some factor less than the charge in C2. So what does that mean about the charge in C3 compared to the charge in the capacitance of C3 compared to the capacitance of C2? Less. So I'll write it down. I really don't like doing this because people just look. But so like C2, right, is like some x times C1, right? Because it's some factor bigger, right? Whatever that number is. C3, you got to be a little bit careful, is some factor less than C2, right? That's what it says if you read the question. So it's got to be C2 divided by whatever the factor is, right? But what is C2 in relation to C1? I mean, you just see it right here, right? And there's a C2 here, right? But can you relate C3 to C1? That's what I'm trying to say. C2 is this, right?
Yeah.
So what do I put X? Right? Is what I'm trying to say. Right?
I don't get. So
The ghost doesn't agree. So you get this, right? C2 divided by Y is C3, right?
Yep.
That's what it says in the problem. It's a little bit hard to understand.
Yes,
The
I
problem.
have it.
Okay, and then C2 is X times C1, right?
Yes.
So what you have is everything related to C1, right? C2 is X times C1. C3 is X divided by Y times C1, right? So then what you do is you put these things back into the equation for the equivalent capacitance. The only thing you don't know is C1, right? Because this is something times C1, this is something times C1. And you found CEQ because you've used the total energy. So the only thing you know is C1. So then you find C1, just algebraically, right? You solve for C1. So now you know what C1 is. And the question is, what's the charge in C3? So if you know C1, how do you find C3?
Find C2 and then you find C3.
Yeah, or you could just do this step.
Oh.
I mean, that's fine. Either way, it's the same thing. So the question is, what's the charge in the third capacitor? So you found C3, you know C3 now. So the question is, if you know C3, how to find the charge in C3?
Just multiply the
C3 times V, right? It's the charge times the voltage. They all have the same voltage because it's in parallel, which is the voltage of the battery. So once again, you find CEQ, first step. You use these equations, which I basically spelled out now, but that's, you know, you're going to hopefully think about it a little bit. Plug it back in here, find C1, right? And then you can easily find C3, it's just multiplying and dividing by a number. And then if you know C3, you multiply it by V, and that gives you the charge in C3. In microcoulomb, so you know, you just got to watch the units, but that's the typical units anyhow. Yeah, it's a little bit of steps, but the steps are pretty, they're not like crazy hard math. Okay, so I was going to say C5. Question 5 is the same sort of question. It's 3 capacitors connected in series to a battery. This time, you know the capacitance values of all 3 of them. But you don't know the battery, the voltage of the battery. But you do know their values initially, and you know how much stored energy they all have. So if they're connected in series, how do you find the equivalent capacitance, do you think, in series, first of all? No, that's in parallel. So
Is it the inverse added into
Mhm.
the
So this
square
is
root?
this is the first thing you should do with the values that you know, at least. And once again, for this problem, you know all these values. So this is just a number, which you can calculate, right? So that's a number. You also know the total stored energy for all 3 capacitors. Again, it's given. So we know CEQ, we know U. What is something we can find if it's a little bit more tricky than this, but naively, if you look at this equation here, again, the same equation we used for the parallel case. You normally don't use this equation, but this is an equation you can also use to find the total stored energy, right? For this case too, in series as well. So in series, you can use any of this, in series or parallel, you can use any of the stored energy equations with the equivalent capacitor, and it'll give you the stored energy. So this is one of the equations we can use for either case. Now, if you know CEQ and U total, which we do know, we know both of these things. Well, you calculate this, but you essentially know this and this. What is the thing you can find?
Voltage.
Right, the voltage of the battery, not the voltage across each capacitor, because it's different for series. The voltage across each one of them is different, but this is the voltage of the battery. Okay, so you can find V, which is the voltage of the battery. That's the first step, right? Okay, Now, what happens is all these capacitors originally have no dielectric. But what happens is you change two of these capacitors. So the first capacitor you bring closer together by a factor of 2, well, by some factor, right? So C1, the capacitor, the distance between the plates changes by some factor, gets smaller by some factor. They get closer together. So what happens to the capacitance of C1? Does it get bigger or smaller? Does anyone remember what the equation is for capacitance?
Wasn't the
Yeah, it's,
distance inverse related?
right, it's epsilon A over D. Anyhow, so yeah, if you bring them closer together, it gets bigger, right? So whatever the factor gets closer together by, that's how much much bigger it gets, right? So you can find the new C1, right? Easy enough, because you know C1. And you just multiply it by the factor, and that gives you the new C1, the new value. And you also insert a dielectric into C2. So what happens when you insert a dielectric into a capacitor? Which is this thing.
Increases.
Right, it increases by the dielectric constant, right? They all have no dielectric constant to begin with. And then you stick one in, which would increase the capacitance, right? So you know the dielectric constant, so you just multiply C2 by the dielectric constant, and that gives you a new C, right? A new capacitance, correct, for C2. C3, you don't do anything to. Only C1 and C2 changes. So the point is, I'm not going to tell you exactly, right out the equation for the new C1 and the new C2, but the point is, you can figure out a new equivalent capacitance, right? Because they're still connected in series. The only thing you do is change the distance between C1, so that makes C1 different by the factor that you change the distance by. And you make C2 different because you insert a dielectric, so you increase C2 by the dielectric constant. So that gives you a new equivalent capacitance, correct? The question is, how much does the stored energy increase by? Not what factor does it change by, but how much does it increase? So what that means is you have to figure out the new U, right? So when you change the capacitance, that changes the equivalent capacitance. So that changes the stored energy. But you can use the same equation. This is the new stored energy. All you do is put the equivalent capacitance, the new equivalent capacitance there. The V you know because you found it already, correct? It's the first thing you found. It's the same battery. That doesn't change. So this is easy to figure out because you know all these things. The CEQ, the V, and what I'm asking is not divide those two things. Like the difference of them. What does that equal, right? So you just subtract this number from the number that was basically given. The original U is given to you in the problem. You use it to find V, right? So you just subtract the new U that you get from the U that was given in the problem, and that gives you how much it increases by, right? So why would it increase by that? If you increase the capacitance, right, that actually would do what to the equivalent capacitance, do you think? So if you increase the individual capacitors, right, values, what does that do to the equivalent capacitance?
Decrease it?
No, it would actually increase it because it goes as the
Yeah.
inverse. Anyway, it's a little bit harder to see. But so the point is, when you make the C's bigger, that increases the CEQ, which increases the total stored energy because the V's the same. So that's why it increases. So this one isn't too bad. This is maybe the easiest one. Well, actually, 3 is pretty easy if you understand it. It's not that much math. I'd say 3 is the easiest, 5 is the next easiest, 4 is the next easiest, and 1 and 2
So
are.
if I increase like C1,
Mm-hmm.
so let's say I increase it from, I increase it 2, that's gonna make it smaller.
Yeah, 1 over that would be smaller, but then in the
Then
end you
you
take
do the
the
square root
inverse
of
makes
it.
it.
Uh,
Yeah, the easiest way to say it is if you increase all of them by the same factor, say x, right?
Yeah.
X, x, x. You factor out the x, right?
Yeah.
So it'd be 1 over x inverse times the equivalent, 1 over C1 plus 1 over C2 plus 1 over C3, which is the equivalent inverse, which is the equivalent. So what I'm trying to say is you'd have this.
Yeah.
You have 1 over X inverse times CEQ, basically. Right? So this would be CEQ prime, which that's X times CEQ. It would be X times bigger. If they all went up by the same factor of X, it'd be X times bigger.
Yeah.
So yeah, it's a little bit hard to see. The math is a little bit harder than the other case, but it generally goes up. All right. Is that good? Okay, so hopefully everyone gets 5. There's so much extra credit on this one. What is there?